So we're talking about magnetic fields, that is the B fields, and we're talking about the forces that get produced when you have a moving charge in a magnetic field. So we're going to talk first of all about a right-hand rule that connects the idea of magnetic fields, the idea of motion of electric charges within those magnetic fields. We'll call it an external field for a moving current. Yeah?
This one?
Is it this one? The question is it this one? There is a right-hand rule, and that's a right hand. So yeah, that's the one.
Yeah.
Yeah, yeah. It's an open palm rule is what it is, yeah.
Wonderful.
All right, so here's the idea. It's part A, we're going to go off in this direction, and we're going to say, well, if I have a wire, and so I'm going to do sort of a cylindrical type thing here, and this is going to represent a wire. And we're going to be drawing three-dimensionally here, okay? So do your best to draw three-dimensionally along with me. We've got a wire here, and it's going off into the distance, and we know that it's receding away from us just because of the little bit of perspective element that I put into the drawing here. And we're going to say that in the foreground, perpendicular to this wire, there's a bar magnet. And the bar magnet has got its north pole facing towards the wire. And then to the right of that, well, let's give ourselves another magnet. But this magnet is going to have its south pole facing towards the wire. And so,
How do you draw a rectangular 3D thing?
Rectangular 3D thing, it's good to start off with a little bit of a slanty parallelogram and recede lines back from it. And then if you want to do a 3D rectangle drawing, you could do a vertical line to do the front edge, and a couple of receding lines back, an angled line, and another receding line that's parallel to the first two. The arrow is just to say, oh, let's go talk about option A. And then we're going to do an arrow over here to say, hey, let's talk about option B now.
Oh, okay. I'm going to make a better arrow.
Okay? But you can just call it part A and part B. It doesn't have to be flowcharty in appearance like mine's going to be. Okay. Alrighty. So we've got a north pole and a south pole, and you guys could tell me what orientation is the B field. From what to what? Remember, I'm really trying to say orientation, not flow, because that's misleading. Nothing's actually moving around here. Yeah. North to south, yeah. So we're going to have a north to south orientation. I'm going to do it just as a dotted line, dotted arrow. B field's going that way. Now, if this is a current carrying wire, you can label it up on your page as a current carrying wire. But if this is a current carrying wire, and the current carrying wire has current that's going, well, and remember, current is the flow of positives, even though it's, you know, conceptually not correct. It's the way that we talk about it as a society anyway. So we're going to talk about the flow of current, not the flow of electrons. We're going to say that this current, this electrical current, never mind the magnetic field for a second, we're going to send a current away from us. So I'm putting an X on the end of this wire so that the current is flowing away from us. We'll label it up as I for current. And so now, before we've talked about right-hand rules where the fingers represent one orientation and a thumb represents another orientation. Remember that? We had two right-hand rules yesterday. We were talking about magnetic fields around conductors in both cases. This right-hand rule talks about what would happen if a flow of charge is moving through a magnetic field. Now, I'm going to back this up with some demos, and I'll show you the real thing. For now, we're going to talk about the theory. I'll back it up with the real thing in a little bit. We're going to have demo day, and we'll show a bunch of demos. But, you know, at this point, you know, take it on faith a little bit. I'm not lying to you. We'll get there. Yes, sir. I think we said. Did we say Monday's demo day? Yeah, we said Monday's demo day. Yeah, Monday demo day, and then we'll have review and tests. A demo day is where we demolish the whole classroom.
I'm down.
No, we demonstrating electromag stuff. Well, I'll get the high voltage power supply and we'll really do some. Oh, because demo could be a short form for demolish as well as demonstrate. Okay, let's keep on moving. We've got things to do and things to talk about. So if I've got myself a nice hand here, and maybe we'll struggle to get the hand drawn properly, but get it started. here's a hand. Okay, we've got a hand with the fingers going this way, and we've got a thumb going off into the background this way. And this is clearly a right hand, and if you want to sort of really show that it's right hand, you can put the knuckles on top.
Still looks so.
There's fingernails now. Got it? I'm not going to do it. Okay, so we've got our right hand, and the right hand has fingers directed in the direction of the external magnetic field. That is the magnetic field that the current finds itself within, and the thumb is pointed in the direction of the current. So this is a three-dimensional diagram, but this is a nice little illustration of what we're going to call our right-hand rule for moving a charge within a magnetic field. A lot of people just call it the motor principle. So I'll put that in writing, okay? Remember, principle is PLE because PAL is your pal, and that's your principal in your school. Yeah?
What does the thing say off of the finger?
What does the what now and the who?
The red thing off of the finger.
This one here?
Yeah.
That's the B field. B with an arrow. Okay, so a current finding itself within in a magnetic field. Now, if you can get a magnetic field to induce, well, we haven't finished this motor principle actually. If you can have a magnetic field in the presence of a current in the presence of a magnetic field, what actually happens here is if you got the current going in this direction, my thumb, the magnetic field going in this direction, the result is, and you can probably tell by the title of the note, the current, or the wire, gets pushed in the direction that your palm is pointing. So there's actually a force. So in this case, this wire would experience a force on it that would be, well, upwards or downwards? Downwards, in this case. Okay, so your palm is in the direction that the conductor would get forced. Okay? Now, if you have a vector going off in one direction, a vector going off in the other direction, and then a third vector, and I said somehow there's some multiplication involved here, people that have done some grade 12 math, do you know, is this a dot product or a cross product likely? Tyler, do you know? Good guess. It was a 50-50 shot, right? It's a cross product. Now, if you're taking grade 12 math next semester, how many people are taking grade 12 next semester? Oh, well, you can look back fondly on this. Calculus. You can look back on this. Yeah, look back on this fondly, and you'll say, "Ah, the cross product." Yeah.
Okay. So
I'm just trying to remember what cross product is.
what if you're looking at it from the bottom? How can you apply the?
If you're looking at it from the bottom.
From the bottom. The north is on the other side.
Well, you know what? We'll look at it from different orientations, and we'll see if the right-hand rule still works.
Basically, what's the distinguishing feature that?
Oh,
lets you orient
do you mean this? What if I looked at this from the bottom? Would I be looking at the south side of this magnet? Is that what you're saying?
No.
Oh,
what
okay.
I mean is, so do you place your hand so that it's pointing in the same direction as the north is pointing? Or do you
Well,
place it so that the thumb, like what is the distinguishing feature that lets you decide where?
So where my fingers point, you mean?
Well, what makes you decide?
Okay, so your fingers point in the direction that the magnetic field is oriented in. And the magnetic field always orients away from the north and towards the south.
And your thumb points to where the current is, so you can turn your hand over.
Yeah, so in this case, the magnetic field is going this way, so my fingers go this way.
So if you swap the north and south magnets, the current would be flowing the
Yeah.
other way.
If I swap the north and south magnets, my fingers would go this way, but the current would still be going this way. And then what would happen to the wire?
Go
It
up.
would get pushed up, yeah. So yeah, you can flip the polarity of the magnets. Absolutely.
So basically, you point your fingers in the direction that the north is pointing, and then from there you point your thumb in the direction that the current is flowing.
Yes.
Okay.
Well, in the direction that the magnetic field is oriented is
Yeah.
yeah. So I want to try and be, precise about the language, but yes, yeah. Cece?
The force exerted, is that the force exerted by the magnetic field?
It's the force exerted on a wire in the presence of that magnetic field.
Okay, so what's exerting the force though?
The magnetic, it's a force field.
Okay. So it is the force exerted by that field then, right?
Yeah. You could say it's a field force. Maybe that works nicely. But we're familiar with the word force field.
Is this what we can?
Yeah.
What if it's two north magnets or two south magnets facing Y?
Oh, well, then you would have the field oriented in some either in some sort of curved orientation or asymptotically or something like that, and then you'd get different forces depending on where the wire was, but it would still obey this rule. It would just have a different shape to the field. This is just nice straight field orientation because there's north and south. No, we're going to deal with nice straight fields, nice uniform fields. Yes, ma'am.
So if you're looking at this one, you're holding it. But if you turn the entire apparatus forward,
Yeah.
your hand would be like this then.
Right, so if we rotated this whole apparatus over, you'd not only... which way do you want to flip it?
Like if you were looking at it from the bottom,
Mm-hmm.
your hand would be like this.
Yeah, if you were looking at it from the bottom, your palm would be turned over, but the thumb would still be... But you'd have to say, look, I'm looking at this thing from the bottom. If I flipped it, I've also flipped the wire. So don't get confused about flipping it. You can always reach into the page and imagine what your hand would do if you're gripping the scenario. Okay. Okay, so this is one option. What we could say is that the motor principle... Oh, Tatiana, one last question? No? Okay. We could say that the motor principle talks about inducing a force. As a result, that's right, of current in a B field. Now, if it's possible to induce a force by placing a current in a magnetic field, you might say, is it possible to somehow change the chain of causation? I can cause a force by letting a current flow in a magnetic field. What if I take the same physical scenario, north, south, oh sorry, what am I doing? North, south, and I take my wire, same wire, I'm not going to write anything about current on it just now. Take my wire and I place it into this magnetic scenario. I know that the magnetic field is flowing somehow through or around the wire like this, from north to south. Okay, so I'm actually drawing the magnetic field flowing, or orienting, sorry, and going around the wire there, above and below. So this magnetic field, what if I take my wire and this time instead of running a current through it, I force it. I actually push it. If I push the wire. So this time what I'd like to say is I'm going to push the wire down and apply a force to my wire. Do you suppose there might be a chain of causation thing here where I can not induce a force by placing a current in a magnetic field, but maybe induce a current by forcing a conductor through a magnetic field?
Yes, sure.
There probably, if I didn't bring it up, it probably wouldn't be an issue, right? Okay? So here's the idea. You can actually force a conductor to move through a magnetic field, and if you force a conductor to move through a magnetic field, you will induce a current. Okay? And it's really an outgrowth of this idea of the right-hand rule. And if you like, you can even start thinking about the idea of action-reaction forces. Because if I have an action, there's going to be a reaction. Here, my action isn't to push current. My action is to push the actual wire. And the reaction is going to be that the wire is going to induce a current. Now, if I push this wire, what direction is the current going to go? What do you say?
Well, it's going to go the same way since you're pushing it downwards. The palm has to face down, so it's going to go out into the background.
Yeah? For sure?
I think so. Why would
Into the background.
no go towards that?
What do you think?
Well, if the force is going down, your palm has to face the way it's going down. Your fingers have to face the way the magnetic field's oriented.
Well, this is something I want to leave to you in a little bit of reading, okay? So we're gonna see how this one behaves, and I want you to do a little bit of background reading on this. But I want to make a note. Come back to this. Okay? What direction is the current going to go? That's the big question that you're going to come back to. Okay? But guarantee there's something going on there. Oh, let's put in an equation here. The equation that governs this rule. Now this guy here would be inducing motion. This one here is inducing current. Well, it obeys another right-hand rule, but let's just call it the current induction rule for now. We're going to induce current with this, and I want you to do the background reading first. The equation that governs both of these guys, once we figure out what direction the current's actually going to flow, it's going to obey this same mathematical calculation, is going to be that the force that's involved here, whether it's a force produced or the force that's being applied, is equal to the amount of charge that's going to be in motion times the velocity at which that charge moves times the intensity of the magnetic field times sine of theta, and I'll tell you what the theta is. The theta is the angle between the direction of current flow and the direction of the magnetic field. Because sometimes the wire isn't perfectly perpendicular to the magnetic field. Sometimes the wire may be at funny angles to it. Okay? Perpendicular is the special case, where sine of 90 is what? 1. So it sort of simplifies out a little bit. That's the nice simple scenario. Sometimes they're not perfectly perpendicular. In fact, in general, they're not. Yeah?
Okay, wait, so the theta is between the magnet
And the current.
that's
The path of the current. Yeah.
now the other thing?
Let me just get to units first, okay?
Okay.
Okay. So for charge, the units are coulombs, which we've discussed before. For velocity, we're talking about meters per second, and we'll get into this in a little bit. And for magnetic field, we're talking about, well, the unit is the Tesla, but the Tesla is a short form for a composite unit, kilogram coulombs per second. Or derived unit of kilogram coulombs per second. Okay? Now if you do all the simplifying out of these units, you'll find that the net units derive out to being units of newtons for force. But I've run out of space on this page. It's just a crossing out exercise, really, so I'm not going to go there. Now,